In the previous example, we had the surface area of a cone, which was dependent on both R and H, and then both R and H were changing as T changed. So we had S, which depended on R and H, and each of those depended on T. So as T changed, R and H changed, which made S change. Now, there's nothing magic about T. We can have plenty of other variables as well. So here's an example where we've got Z depending on X and Y. So in my notation above, Z would depend on X and Y, and X and Y both depend on R and theta. Okay, so if R and theta change, then X and Y will change, which will make Z change. So what we're trying to figure out is how does Z change as R changes, and how does Z change as theta changes. Okay, so it's just the chain rule again. So dz dr is going to be how does Z change as X changes times the relationship between X and R, plus how does Z change as Y changes times the relationship between Y and R. And then it's just a matter of working out each of these things. Okay, so we have to do our partial derivative. So the partial derivative of Z with regards to X is just 2X. And then if we differentiate X with regards to R, we're just going to end up with cos theta. And then we do Z with regards to Y, it gives us 2Y. And Y with regards to R is going to give us sine 2 theta. Okay, and given that this is, we're trying to work out things with regards to R's and thetas, we don't really want X's and Y's in them because they're going to change as R and theta changes. So we just make some simple substitutions. So instead of X, we can flip in R cos theta. So we get 2R cos theta times cos theta, plus 2Y is R sine 2 theta, and there's another sine 2 theta there as well. So we end up with that. So we could factor out the 2 R's, and we're left with cos squared theta plus sine squared 2 theta. Okay, so this is how Z changes as R changes, because it does depend on theta, but we're assuming that theta is fixed for a while, and we can work out as R changes, that's how Z will change. And then we can do exactly the same for finding how Z changes as theta changes. So it's going to be, turn the video off if you want to have a go at doing it yourself, and once you're back, this should be what you're doing. Okay, and so as Z changes as regards to X, multiplied by how X is affected by theta, and then the same for the Y component. So partial Z partial X is 2X times partial X partial theta. So now how does this thing change if we are using, if we differentiate as regards to theta, so cos differentiates to negative sign, so it's going to be negative R sine theta, plus change of Z with Y is 2Y, times Y with theta is going to be 2R cos theta. And then again, substituting X's for R's and thetas, we get negative 2 R squared sine squared theta. No, we don't, that's a massive lie, because X is R cos theta, so it should be R cos theta times R sine theta, so it should be R sine theta cos theta, plus 2 lots of Y, which is R, 2 times 2 is 4, I'm starting to lose it now. Y is R sine 2 theta, and here we've got, I really am losing it, so we've got R squared sine 2 theta cos 2 theta, which we can probably simplify a little bit. Let's take a 2R squared out the front, sine 2 theta cos 2 theta minus sine theta cos theta. And you could probably try and tidy it up a little bit if you wanted to. Well, you'd need to, because there should be a 2 there for a start to get that 4 to work out. I think that worked out, so look at it, check out, I think I've got it right, see where I adjusted things as I went, but it should work out, I think.